Welcome back, everyone, for the second day of 3 Rand workshop. We had a wonderful first day, full packed of a lot of exciting talks and a panel, very nice discussions, questions, exchanges. We hope to continue that to the second day as well. So let me just briefly show the agenda for today. So we start our session 3 because a couple of sessions were done yesterday with randomness beacons. It'll be 3 talks, and then we'll take a short break for 15 minutes. And after that, we have a slightly longer sessions, more packed of more talks. There will be 4 talks on future of decentralized randomness and related topics, consisting of different emerging, different verifiable randomness trends, and some other topics such as threshold signing, very relevant, right? After that, we'll have another 15 minutes break. And finally, we'll have a research focused panel to complement yesterday's industry focused panel to discuss different kind of problems and emerging research in on-chain randomness space. That will be moderated by Aniket. All right, then let's get started. So the first talk will be by Joe Bonneau. So Joe, can you share your slide? Let me stop sharing.
Okay, can you all see my slides there?
Yes, and we can hear you.
Great, shall I begin?
Yeah, so let me just. So the first talk is by Joseph Bonneau, who is an assistant professor at NYU and also affiliated with A16Z. The talk will be on Cornucopia distributed randomness beacons at scale. Over to you, Joe.
Okay, thanks a lot. Good to see everybody. So this talk is a joint work in the last year with my PhD student Kevin at NYU, as well as Miranda, who's a PhD student at Columbia. Okay, so great for this audience. I don't have to explain what a randomness beacon is at this point. Hopefully there were enough definitions yesterday. But to give you an idea of where we're going here, here's, I think, a hierarchy of randomness beacons. So we heard about some centralized beacons yesterday that require a trusted authority, moving to some beacons that require a set of authorities like DRAND, where you have to trust that a majority of the nodes are honest. If you want to get to a beacon that tolerates a dishonest majority, so you're asking people to trust just that not every one of the authorities is dishonest, the only way that we really know how to do that, I should say, trusted hardware or delay functions, which is a topic that I've spent quite a bit of time working on. And this talk is about taking the next step beyond even that, what I would call a participatory beacon, where we don't even ask users, here's a set of authorities, trust that not all of them are dishonest, but we actually say anybody can join the protocol, open participation. So you could think of it as being permissionless would be another word. And then you only have to trust yourself. So you participate yourself, and then you don't have to trust anybody else, and you can be convinced that the output is actually random. Okay, again, we want to build a protocol that is secure even if n-1 out of n nodes are malicious. And I claim that this is a special case. And the reason is that at that point, participants don't care who else is participating. You don't need to know who the other participants even are, or even the number of other participants. All you need to be convinced of is the fact that you were able to participate, if you trust that you're honest. Now, sometimes people make some caveats here and they say, you can't always be sure that you yourself are honest because your machine might be compromised, which is true, but we'll assume for now that you trust that you have an uncompromised machine and you're able to participate in the protocol genuinely. So if you achieve that property that you only need one honest participant, then the observation is that there's no security reason to limit who's participating, right? You don't get any benefit security-wise from keeping extra participants out. Extra participants can never hurt you, right? They can only increase the chance that at least one of them is honest. So the only reason you would ever limit the participant set is for performance reasons. And if we can make it practical, scalable to open up participation to anybody, then you get into this really good state where anybody can participate and only have to trust themselves. So To get there, I told you that we want to use delay functions. So we'll build off this unicorn idea, which some of you have no doubt seen before, a very simple randomness beacon. So it requires some either reliable broadcast channel or a public bulletin board. You have a number of users. They each just publish a random contribution. So there's no commitment here. There's no signatures or threshold crypto or anything fancy. Everyone just publishes a random string. You concatenate everybody's random string. You pass the result through a delay function. The delay function is really the only cryptography at all in this protocol, besides whatever you need to set up the bulletin board. And the delay function is really doing all the work. And the security model here, the reason that this actually works is that even the last participant to publish, or a coalition of last participants to publish who can see everybody else's contributions, they can't compute the delay function fast enough to grind over possible contributions and see what their result will be. The best that they can do is pick randomly. If they don't pick randomly, it doesn't matter as long as at least one of these things is random. And again, as long as the delay function takes long enough to compute, much longer than whatever the deadline there is to participate in the protocol, then it's not possible to actually intelligently influence the output by varying your own contribution. So this is great. It's secure if any of these users is honest. The only problem here is that it requires everybody to broadcast their contribution. So it's already very efficient as randomness beacons go. It just requires everybody to publish a short random string. But again, if we want this to be a totally permissionless thing, imagine millions of people participating. All of a sudden, this is not going to be practical. Specifically, you could think about running this on top of a public blockchain in L1, maybe like Ethereum. The dream would be that everybody buying a lottery ticket or everybody playing an online game would all participate in the protocol. And that's probably not going to be practical if everybody has to Ethereum L1 every time the beacon happens. Not if you want to have millions of participants, right? That would be a very expensive protocol. So really the main question in the current work, Cornucopia, is can we do the same thing or approximate the same idea as Unicorn, but not require everybody to publish something? So the way we do it is we add a coordinator. You can think of this as like a roll-up server for a randomness protocol. And the coordinator is going to combine everybody's contribution before it gets published. So just like before, everybody participating just gives a short random string. But this time, the coordinator is going to accumulate all those contributions. So it's going to respond to each participant with an inclusion proof. And then it's going to publish a set commitment to everybody's contributions, an accumulator value, to the bulletin board. Now, this diagram may be slightly confusing. The commitment has to be published. This would be published in two steps. The commitment first, because that has to come by a deadline, and then the result is available later, obviously, after the delay function is computed. But okay, so when you participate, you have to verify two things now if you're an observer. First, you have to verify that your contribution was actually included in this commitment. So you could think of that as verifying an accumulator proof or a Merkle inclusion proof, something like that. And then you verify that the delay function was computed quickly. Of course, if it's a verifiable delay function, a VDF, this should be efficient to do. So those are the only two things that you have to check. Notice you don't check anything about what anybody else did. You don't care. You just have to check that your contribution was included. To get to what I would call a participatory randomness beacon, we need not only this dishonest majority security property, but communication-wise, we want at most a logarithmic amount of data to be published, and the number of participants constant is also achievable and great. Similarly, for computation, we want not a linear amount of work per user so that it's efficient for individual users. We don't make the same assumption about the coordinator. They're going to have to perform at least linear work. They have to talk to everybody. They have to give everybody an inclusion proof. So we can't get around the coordinator needing to do a lot of work here. The coordinator is semi-trusted, and I'll come back to this. So they can harm liveness of the protocol. They can't undermine security. They can't predict or manipulate. What they can do, and again, we'll come back to this, is potentially pull off a censorship attack. Okay, so the way that we actually build a protocol like this, very straightforward. This idea was not new to our paper here. It's appeared at least in this Head Start paper, and I think in others as well, that you just have everybody publish a contribution. The coordinator uses a cryptographic accumulator, a set commitment, Every user has to receive their proof quickly before the deadline so that they're convinced the coordinator hasn't had enough time to potentially compute the delay function. And then after this delay period, everybody checks the result, like I said. So how do we prove that this is secure? It's easy to convince every user that their randomness was actually included. That is just the fact that the accumulator works. If the coordinator wants to actually cheat here, their task specifically, they have to find some commitment value, which includes for any given user, they have to be able to compute an inclusion proof to convince them that it's included. But they have to do this before they actually know people's contributions. So the only thing the coordinator can do if the delay function is secure, they can pre-compute some different possible commitments, but they have to pre-compute some commitment that they can then prove arbitrary items are included in. So when we first sat down to do this, we thought it would be a straightforward security proof from existing accumulator security definitions. You shouldn't be able to prove that something's included if it hasn't actually been included. That's basic accumulator security. But it turns out you need a different property here that nobody had ever considered before, as far as we know, because there's a very specific attack on this protocol, which is very simple. The coordinator, that is, can just try to accumulate everything. So if they can accumulate the entire data universe, they can pre-compute the delay function, and then they can convince anybody that whatever random contribution they give has been included. And it turns out standard accumulators don't actually rule out this attack, so we had to make up a new security property. Fortunately, it's very simple. It's a very simple game-based definition. The adversary, who would be the coordinator here, has to commit to an accumulator value. The challenger then sends a random value. This would be like a user's random contribution. And the adversary has to convince the challenger that it was included. So notice they have to convince the challenger here that their item was included, and they committed to the accumulated value before they saw this item. So again, conceptually, what the adversary has to do to win this game is accumulate the entire data universe, or at least an exponentially sized portion of it. Okay, we prove in the paper that this is exactly the security condition you need. We prove this cornucopia protocol flow is secure if you have an accumulator with insertion security and a secure VDF. And we also prove in the other direction that if you have a participatory beacon that's secure, you have to have an insertion secure accumulator. That's the only way to do it with kind of sublinear communication. So that's nice. It's a tight security property. The other thing that sort of popped out of this, which was nice, is that you get a very simple security proof for Unicorn, the kind of classic protocol, which you can view as a special case of this with a very inefficient accumulator that's just posting a concatenation of the set. So you could ask, is every accumulator insertion secure? It seems like a pretty natural thing that it's difficult to accumulate an exponential number of items. Turns out, no, you can easily define accumulators that don't have this property. One is if they just have a special symbol that's defined to be the accumulation of everything. It turns out RSA accumulators actually have this. If you don't do any extra work, you can publish an accumulator value of 1 and then prove that every item is included. In the proof, we have to rule out the value of 1. But maybe something less trivial, you could define this range accumulator idea that lets you just publish 2 items and say everything between them is in the accumulator. And then you could also break insertion security. Okay, I see a long question. I think I'll maybe come back to that at the end so that I can finish here. Okay, so we also prove in the opposite direction, you can have an insertion secure construction that's not actually a secure accumulator. So this is just to show that these two properties are actually different. You can definitely have standard security without insertion security and vice versa. All right, so that's a lot of technical trivia there. The important thing, the good news, is that basically every accumulator that we know of is insertion secure pretty much out of the box or with minor changes. So you can use a Merkle tree, you can use an RSA accumulator, bilinear accumulator, you can use KZG commitments. All of those work in this model. You can build this protocol and it's secure. And the paper has a specific security reduction for each of them with basically standard security assumptions. And there's only a few minor tweaks. Like I said, with RSA, you have to rule out this special value. And similarly for the bilinear accumulator, the Merkle tree just works out of the box. We showed you can basically do this, and the existing accumulators are secure. We just had to define a new property to show it. We also show a second result, which maybe isn't super interesting because the standard accumulators already have this property, but you can also build an insertion secure accumulator from any accumulator that's universal, which means it supports non-membership proofs. It's inefficient and a lot of work to get there, but this is just to show that there is a standard transformation that builds this property. And okay, so the last thing that I wanted to get to, I hope I'm not over time. Just give me a poke if I am. What happens if the
it's fine. Just 2-3 minutes is okay. Yeah.
Okay, great. So what happens if the coordinator is malicious? Imagine you have every n-1 participants are dishonest. You also have a dishonest coordinator. The one thing the coordinator can do is they can just censor, right? They can just pick a specific user and not include their contribution. Now, they can't trick the user into thinking that they've participated, so the user will know that this censorship happened and that they weren't able to participate. Maybe they could complain on Twitter or X, who knows, Farcaster, but they can't really prove that they've been censored. The coordinator can obviously just claim they never received the contribution. So the best thing that we can do is add multiple coordinators, and it's actually fairly simple. You add multiple coordinators, users submit their contribution to everybody. They can actually use the same contribution, doesn't have to be different. Some of those coordinators might censor, but as long as you have one honest coordinator who includes your contribution, gives you a proof, all the coordinators submit a commitment now to the bulletin board, and then the output of the randomness function, you concatenate all the commitments, run them through a delay function, and you're done. And the property you get, you add C coordinators. It's multiplying your broadcast cost by C, but the protocol is live as long as at least one of the coordinators is honest. So you could think the number of coordinators might be a handful. If all of them are dishonest, you'll know and not to trust the process. And you really just need one honest coordinator and one honest user for this to work. Okay, so that's what I wanted to share, and I'll take as many questions as we have time for, being mindful of the schedule, and the paper's online if you are interested in reading it. Okay, so let's see.
Yeah, there are 2 in the chat box. By the way, thanks a lot for the nice talk. There are 2 in the chat box and 1 in the Q&A, whichever you want to answer.
Okay, sure.
I think the first one in the chat.
This slide is addressing Luis's question has been already addressed. So maybe you can just take up the next one, Kostas's question.
Okay, let's see. Do participants contribute by posting some random nonce, or their contribution can be predictable? If it's random, so they do publish something totally random, it's not tied to their nonce or anything like that. How the security definition of a malicious coordinator preparing a universe accumulator applies as an attack we should defend against in the first place. I'm not sure I really understand the question, Costas, if you're online.
Can I ask a question? So in one of your slides, you mentioned that one new attack definition you defined in the paper is the fact that a malicious coordinator can prepare an accumulator of the whole universe.
Yeah.
And then can prove that you have like inclusion proofs on something that I already pre-prepared. Is this a real attack? How can they even prepare a universal?
It's not, it's only a real attack on certain accumulators that make that efficient, but that was the whole aim of the insertion security, and the proof in the paper is to show that for standard accumulators, you can't do this efficiently, right? You can't compute a security with the whole universe in it.
Okay, so that's what you're proving, right? There is no ideal accumulator for this. That's the proof you're providing.
Yeah, you can define an accumulator that makes it easy to accumulate the whole universe, but the good news, again, standard accumulators don't, although. So there's a question from Benny in the QA. If the adversary does not know the RSA trapdoor, even if the adversary doesn't know the RSA trapdoor, he can produce a digest and prove anything is in it. I'm not sure how, Benny. We mentioned the special case. There's the degenerative case where the value is 1. Otherwise, if you don't know the group order, you can't produce an accumulator and that accumulate and then produce proofs for arbitrary random elements. I'm not sure if Benny's online. Oh yeah, go ahead.
No, I don't think we have to probably ask him to join on the panel because he can't speak.
I think
Okay.
Yeah, it's not on the panel. But yeah, I think if Benny wants to reply, I think you can ask another question on the box. In the meantime, Alan has a thought that I think the streaming authenticated data structures.
That's a good point. We should add it to the paper. We haven't looked, but it's good to see. I think it's interesting to see if that's another thing that doesn't have the property.
All right, then. So I guess thanks a lot, Joe. It's pretty great. A lot of engagement. So I guess the next talk is by Akhil.
So I guess we'll be running by 10 minutes just so that then everybody gets things. So it's fine. We can keep that in the break shorter.
Yeah, that's fine. That's fine. Yeah. So Akhil, are you there? Can you share your slides, please?
Sure.
Turn on your video.
Video is on. Can you hear me?
Yeah. Yes, we can. Sure. Can you share your slide, please?
Sure. Just give me a moment. Can you?
Perfect. Yeah, just make it a show, like slideshow.
Yeah.
All right. So the next talk will be given by Akhil Bandarupalli, and he is going to talk about HashRand, efficient asynchronous random beacon without threshold cryptographic setup. Sounds pretty exciting, and it's accepted to ACM CCS 24, yet to happen in Salt Lake City. Okay, Akhil, over to you.
Okay. Yeah. Hi, everyone. Very good morning to people in the US. Very good evening to people in India. Yeah, I'll talk about our recent work, HashRand, efficient asynchronous random beacon without any threshold cryptographic setup. Yeah. A random beacon is a source of secure randomness. But yeah, it emits regular random numbers at regular intervals. So it's analogous to a house emitting beacons of light at a periodic interval. So it has multiple applications in like DeFi and GameFi apps on blockchains. There are smart contracts that invoke secure randomness. In many applications, it is used for secure committee election in like proof of stake blockchains, where randomness is fundamental to the security of the protocol itself. And it's also very useful in asynchronous SMR, state machine replication, and multi-party computation protocols, where distributed randomness is often required to overcome the FLP impossibility. Popular sources of randomness exist, like there are centralized sources of randomness like random.org and NIST Beacon that exist. It's like there is a user who wants randomness, he just goes to the website random.org and he requests randomness from there. But yeah, it constitutes a central point of failure. If an adversary takes over the website, then yeah, the user does not get a secure random number, but he instead gets something that is chosen by the adversary. So distributed random beacon protocols fill up this gap and eliminate the central point of failure by distributing trust across multiple nodes. The adversary, so this kind of beacon protocol is resilient to a fraction of nodes being taken over by the adversary, and yet continues to produce secure, unpredictable randomness. So I'll briefly define the problem. A distributed random beacon protocol B running among n nodes produces outputs of the form x, bx. Oh, sorry. Yeah, x, bx, where x is a natural number. X is an index that is on the list of natural numbers, and bx is a random element from the domain D. So for example, yeah, like this. For example, like this, the number 432 is a random number generated at index number 1. So the protocol B must satisfy 3 basic properties. First is agreement. The honest nodes must always agree on the beacon value for every index, for every natural number index. And liveness, honest nodes must eventually output a beacon for all x greater than or equal to 1, like from 1 to infinite. Like no beacon should not, at no natural number index, the honest number should not fail to produce a beacon. Like the beacon needs to keep growing, And bias resistance and unpredictability, the adversary must not be able to bias the value of or predict any beacon without the honest nodes giving their consent to reconstruct the beacon for that particular index. Yeah, the adversary should not basically know anything about it until an honest node starts reconstructing. And once it reconstructs, only then the adversary and everybody else should be able to beacon value. So yeah, here the domain is 1000 from 1 to 1000. And the indices are natural numbers, and it must keep going on. So this is the basic definition of the problem. I simplified it a lot for the sake of simplicity of the talk, but the definition has probabilities, like the high probability agreement must hold. Yeah, prior distributed random beacon protocols like DRAND, for example, that's one of the one of the first protocols that appeared in the space with a practical implementation. It uses N-T threshold unique signatures for beacon generation, where these protocols require a threshold setup where nodes must possess secret shares of a uniformly random public key. In this protocol, each node signs a partial signature, and every node waits for T+1 threshold signatures and accumulates them to produce a pseudo-random string. The threshold setup can be established using a distributed key generation protocol, but it is very expensive to run in practice. And even in settings like proof of stake, where the committees need to keep changing at regular intervals, and running DKG can be very expensive, and it's also a very strong setup assumption on the system. There exists other protocols in the space that get rid of the threshold setup assumption. OptRand and SPERT are two examples, with OptRand being a synchronous beacon and SPERT being a partially synchronous beacon. So the template of these protocols is as follows. Honest nodes use a primitive called verifiable secret sharing, VSS, to distribute secret shares of a uniformly random value. For participants, each node picks a random value and uses verifiable secret sharing to distribute secret shares of its picked secret. So the idea is only at least T+1 parties need to come together to reconstruct that value, and only the faulty party cannot basically know anything about what the honest node's secret shared just by looking at its own secret share. Then they use state machine replication, an agreement primitive, to agree on a set of T+1 nodes who shared their secrets successfully. Yeah, the nodes then run SMR, and then they agree on a list of T+1 indices that have shared their secrets successfully. So say here it is 1 and 4, for example. And only after the SMR terminates, the honest nodes reconstruct the secrets that were output in SMR, and then they create the secrets that aggregate the reconstructed secrets as by adding them and outputting the value that's in the green box. So the idea is why this is unpredictable is the adversary does not know anything about the secret shared by R1 until after agreement on one is over. It cannot decide its secret after observing what node 1 or any other node that was part of the agreement set in the SMR. Like, it cannot adaptively select a secret by looking at what others reconstructed because by then agreement has already terminated. So this is a standard template that traditional beacon protocols follow. But coming to an asynchronous random beacon, we note a few challenges. In an asynchronous network, SMR, state machine replication, or Byzantine agreement is bound by the FLP impossibility result. This says that the FLP impossibility says that it is impossible to achieve a consensus even in the presence of one single crash fault in an asynchronous network. But this impossibility is circumvented traditionally using a random beacon protocol, and this creates a form of circularity. Like, for SMR, you need a random beacon, and for random beacon itself, you need SMR. So this creates a circularity because of which this design is basically unusable in asynchrony. And the other major challenge on top of this circularity is that the random beacon protocol in asynchrony requires an efficient asynchronous verifiable secret sharing AVSS protocol. Contemporary AVSS schemes like 7 use computationally expensive discrete log cryptography and bilinear pairings. So we observe that the computational complexity of AVSS is a major bottleneck in creating and generating beacons at a high throughput. So each beacon in prior protocols like OptRand and SPERT require n square exponentiations per beacon, which we show is very expensive in terms of computational complexity. And of course, it is not post-quantum secure because it depends on the discrete log hardness assumption, which is not secure in a post-quantum world. So these are the main challenges, and we'll present a brief. We'll present how we overcome that question. I'll answer.
You can answer the question.
Yeah.
at the end.
There are two challenges. We circumvent these challenges using, like the first challenge, we circumvent the beacon SMR circularity using an efficient approximate agreement protocol. So approximate agreement protocols do not require random beacons because they have a different way of circumventing FLP. Like nodes do not exactly agree on a value, but they approximately agree. What I mean by approximately agree is there is a parameter called epsilon, which is called the agreement distance, and honest nodes outputs must always be within an epsilon distance of each other. So this is the termination condition for all. Yeah. So an approximate agreement protocol does not require a beacon to or circumvent the FLP impossibility. So of course, the approximate nature of agreement in our protocol results in a non-zero probability that honest nodes disagree on the beacon output. Like they can disagree with a non-zero probability. And we will show how to tune that probability and make it very small in practical settings so that you don't have to worry about that disagreement. And for the second challenge, we address the high computation of prior beacons by using hash-based verifiable secret sharing. The reason we introduce hash functions is hash functions are computationally much more efficient than discrete log exponentiations. Like they are at least 1,000 times faster and cheaper than discrete log exponentiations. If it takes 70 microseconds to execute a discrete log exponentiation, a hash function basically takes 70 nanoseconds, a hardware accelerated hash function. Deal with the loss of homomorphism. Discrete log exponentiations are homomorphic. So we deal with the loss of the homomorphism by weakening the AVSS primitive by proposing an asynchronous weak verifiable secret sharing protocol, which only uses hash functions. So we'll explain later how we are dealing with this loss of homomorphism. So in comparison with prior works, I'd like to note the computational complexity in terms of this number of discrete log exponentiation needed. We replace discrete log exponentiations with hash computations, and we show that this is the reason for computation efficiency. And yeah, the communication complexity is lambda n log n per beacon.
Just to confirm that you're ready, so maybe
Sure,
try
sure.
to wrap up in a couple of minutes. Yeah.
Sure, yeah. The design overview, we built HashRand on an approximate common coin primitive. I'll briefly explain how this works. They exist for the nodes. They use AVSS to share a random secret, and they use a distributed computing primitive called gather, which acts as a distributed commitment, a form of distributed commitment. And then after terminating gather, they run 4 approximate agreement instances, one for each node. So if a node's AVSS was successful if node i's AVSS was successful at node J, then it would input 1 to the approximate agreement and input 0 otherwise. This approximate agreement protocol runs for R rounds, after which the honest nodes start reconstructing the protocol. And WI here, then after reconstruction, they aggregate the secrets similar to how it was in VSS, in the VSS SMR primitive, but except for the fact that the weight here is the output weight that comes from approximate agreement. So W1 is the output of AA1, W2 is the output of AA2, and so on. So this is the basic primitive. The gather primitive here ensures that honest nodes commit enough secrets such that the adversary cannot look at them and adjust its secret later on. Yeah, basically the weights are at most epsilon distance from each other. So the honest nodes basically output an interval of, if you map the outputs of honest nodes, they are going to be an interval. But that interval basically is random. That epsilon sized interval is completely randomly chosen from the entire domain. So what they do is they round their output off to the closest checkpoint. So here D, 2D, 3D are the checkpoints. So this results in a small yet finite probability of disagreement amongst honest nodes. So if the interval is basically at the midpoint, for example, they'll round it off to completely different checkpoints. So that would cause disagreement, but that probability can be minimized by minimizing the ratio epsilon by d. So the smaller that ratio is, the smaller the probability of disagreement is. Yeah, and that requires running more rounds of approximate agreement. But this doesn't affect our protocol because we pipeline the instances such that beacons are produced at a consistent rate.
So you have to really run now because
Yeah.
I think we are already. So you can just talk about the probably end result and then finish it off.
Okay. Yeah. This is a hash-based weak verifiable secret sharing protocol. Like we use batching. In this case, we replace AVSS with badged AWVSS. The difference between AVSS and AWVSS is in AWVSS you can reconstruct bottom, which indicates a malicious relay, whereas in AVSS you always reconstruct a secret from the field. Yeah, the cost of gather plus approximate agreement is amortized over all the secrets in the batch, but it still is kappa and q log n. So we use this anytrust sampling technique that will reduce communication. So here we basically sample nodes and we only run approximate agreement instances for the nodes that were picked in the sample. And the idea is the randomness of the output can be ensured by the contribution of one honest node's contribution is enough. So the sample needs to be anytrust. So the sample size is really small. And this allows us to overcome the n-cube bottleneck and it brings it down to n square. Yeah, this can be applied to a post-quantum SMR protocol. We implement it for Tusk by replacing EDDSA with large-based dilithium signatures. So the evaluation.
Yeah, you have to really stop now. You have to just go to the end slide. You can't show, right? Because you're already running like 10 minutes late now.
Yeah. This is the result. So this is the last slide. This is the result. HashRand is the computational complexity clearly allows it to outperform SPERT, another n square discrete log beacon, whereas Definity DVRF is a threshold signature based beacon, which only has linear computation complexity. So it is vastly superior. The computational efficiency allows it to perform much better. And post-quantum SMR, this is the...
Yeah, we have to you can just go to end slide and finish it. I already tried to answer the question so we can move on because otherwise we have to just basically stop the break, right?
Yeah, that's fine. We can just delay by 5 minutes. There is one question like Amit asked in the Q&A, can the adversary influence which final value gets selected as the random beacon from the small epsilon sized random range?
Yeah, so thanks for the question. The answer is no, because the gather primitive allows at least f plus my honest nodes inputs to be part of the final aggregation. And the honest nodes do not start the final aggregation until after terminating all approximate agreement instances. So the adversary can choose his secrets based on what the output is, but since the weights are already approximately agreed upon, the contribution of his chosen secret will be very small based on the epsilon limit, and it's not enough to bias the beacon.
All right, I think we can go to the next talk. Thanks a lot, Akhil. It's pretty elaborated. And there is one more question. I think you can just type it there in the Q&A. So we move to the next talk, the final talk of the first session of the second day. OptRand, statistically responsive distributed random beacons, will be given by Adithya Bhat from Visa Research. Adithya, over to you. Oh, you are muted. Can you please unmute?
Okay, am I audible now?
Yep, please.
Okay. Thank you so much, Pratik, for the introduction. And thanks for the opportunity. Today I'll be talking about OptRand. This is going to be a lightning talk. Let's see how fast I can convince you guys and explain to you what OptRand is. This is a work with my collaborators Nibesh, Aniket, and Karthik. Okay, let's dive in. Let's try to understand what the requirements are, what we're trying to design here, because I think we have been motivated enough on what random beacons are in this session. So when we say responsive, we usually mean that whatever protocol we're building, it works at network speed. It is not using some fixed timeouts. So as long as you can get messages, you can make progress. When we say optimistically responsive, it's responsiveness under some conditions, optimistic, some good conditions. When we say distributed, we mean that there is no fixed one party that centralized or a trusted party that controls any behavior of the protocol. By random beacon, we say that, okay, I'm just trying to figure out how to hide this panel. Give me 1 second. Let me put it on top. Yeah, so by random beacon, I mean that our protocol should output some numbers for every round. There is a fixed counter called a round, and whatever the numbers that it outputs, it should be unpredictable. So there's nobody, no adversary there, or anybody can predict the beacon before it's done. And bias resistance means that nobody can influence it away from a uniform distribution. So the numbers should appear to be from a uniform distribution. Some additional properties that we would nice to have would be optimal fault tolerance, right? If you take, in our case, we'll be in bounded synchrony, we want half fault tolerance. We should not compromise on the fault tolerance. We want optimal communication complexity also. So we want to not spend too much energy, too much time, too much messages in our protocol. We also want the latencies to be small. So you do not want to wait too long for your beacon. And we want reconfiguration friendliness. So this is a new property, which means that you cannot tie the whole system to some form of a setup, which you need to redo every time you change the parties. So reconfiguration friendly protocols will allow you to seamlessly add or remove nodes. Okay, so some more context on the adversary. Adversary is always TPT. We assume T is the number of Byzantine servers. We denote by F as the actual faults. So F is usually less than T. And the corruption can be static or adaptive depending on the protocol. So we just assume that the corruption is static for now. And the adversary is rushing. Adversary can view all the messages in the system. So some of the network assumptions that we make in our protocol is delta bounded synchrony. So it means that if somebody sends a message at time t, if in some universal clock, then you know that everybody will receive the message by time t plus delta. So whoever the recipient is. And we use this small delta to denote the actual network speed. So let's say capital delta is 10 minutes, small delta may be a millisecond. So when you actually send the message, it takes a millisecond, but you are assume worst case assumption is 10 minutes. And we assume that servers can be in different rounds as opposed to classical synchronous protocols. We just know different nodes can be in different rounds. We don't assume that they should all be in the same round. Okay, some of the cryptographic assumptions that we make is we assume PKI and digital signatures. We assume random markers. We assume the QSTH assumption, which is just a tuple of this form. And okay, now let's dive right in to learn how OptRand works. So we'll start with the round-based protocol. So in every round, we'll have some parties. So we, in this example, n is 5, and you have t equal to 2 Byzantine faults. Since we want optimal fault tolerance, this is the max you can tolerate in our setting. So you have 2 Byzantine servers. What we'll do is in every round, everybody will toss some internal coins, perhaps take contributions from the public, do something, collect some number, and decide on a random number, and they're going to lock it in a box. So this box is a PVSS box. Okay. So all servers are going to do this in the system. What they're going to do is their local version, local randomness, they're going to send it to a dedicated person called the leader for that round. So they'll send this random number. Now the leader has to somehow mix the PVSS from multiple servers, multiple nodes, and build what we call as a publicly verifiable random share. It's a PVRS. It's a sharing for NT sharing of a it's a string that proves that this is a random number, i.e. contains inputs from t plus 1 people. Okay, once this leader mixes these, this is a very high level language. So once he mixes these random numbers, it's going to input it into a state machine replication protocol. So this state machine replication protocol, now once we have the state machine replication protocol, this will handle what happens when the leader fails and the leader puts wrong strings, how to ensure low latency, all of that will be handled by the SMR. So I will talk today on the first few aspects, and the SMR, I will just tell you what we have in our result. So today I'll be concentrating on 1, 2, and 3. Okay, so let's understand the PVSS, publicly verifiable secret sharing structure of how a PVSS looks like. So there'll usually be encryptions for every person, encryption of an evaluation of a polynomial, which contains a secret. There will be a commitment to the polynomial itself and a proof that everybody's shares are correct. So this is the general structure of a PVSS. Usually the encryptions are homomorphic. So if you take 2 PVSs from 2 different people, you can add the encryptions together. Nothing. It will be the result of the summation of the secrets. Commitments also add up. Unfortunately, the proof does not add up generally. So this is the problem for our approach, right? Where everybody signs it to a leader cannot add it. So the problem will be if he adds it, if he mushes it together, the input string becomes of NT size, which is too big for optimal communication complexity. So what we do is, after doing some research, we found that Scrape has this pairing based VSS where the proof becomes a pairing check. And now everything is homomorphic because pairing check you can do even if you mix and match together. But there's a new problem, right? So since it's an adversary, it's a leader that is collecting inputs from all the servers. What he can do is he can take some honest inputs, combine all of them, generate a negative of that, right? Like you can just multiply with -1 and get a correct sharing and tell that's a contribution from another Byzantine guy. Now, when you add them, the result is 0, right? So, and then another, you can use another Byzantine server to add any number you want. So you can bias it basically to any favorable number. So we need some mechanism to pin each contribution, somehow make sure these contributions are not malleable in some sense. So how do we do that, right? I think cryptographers might be jumping in their seats at this point because what we do, our core idea here is to add decomposition proofs. So in general, it's not just applicable to PVSs. You can take any homomorphic object, let's say its size is L. If you can create a verifiable homomorphic tag for that object. So in this example, object is a PVSs. So a tag will be a small element that can be linked to this homomorphic object. So usually of size kappa. And what we'll do is you can mix the M homomorphic object with the same size, right? That's the whole property of homomorphism of the object. But the decomposition proof can be just a signature, something that pins each contribution on the tag, on the homomorphic tag. So now you have M kappa signatures. And this whole thing can serve as a proof that these individual parties contributed these pieces, these tags. And you can combine the tags on your own and check that the final homomorphic mixed string is of the correct tag. And this idea, we call it as a decomposition proof. So to be technically and pedantically correct, I will just use the bit vector and log m terms, but it's not important. So the total size is actually L plus log m plus n kappa. This is the key idea of OptRand, of the cryptographic aspects of OptRand. So concretely, what we do is we use Scrape pairing-based PVSS as a homomorphic object. So this will be our homomorphic object. The tag, we'll just use it as the evaluation of the polynomial at 0. So that will be the tag. And what happens is, what we do, as we described in the overview, is we take t+1 contributions and we merge them together and use the decomposition proofs, and we call this as a publicly verifiable random shell. And this size is n kappa. N kappa, now once we have an n kappa sized input for every round, what we can do is we start focusing on the SMR aspect. So the SMR aspect needs bias resistance, since we need a beacon for every round. So it has to be the case that the SMR should tolerate a rotating leader. It cannot use the fact that you have the same leader doing the same thing again and again. Because we want optimistic responsiveness, we need a way for a server to convince the other servers to catch up to a new round. So we need a small object that we can tell, saying that, hey, look, come, let's all, the latest round is around 100, please catch up. So we need like a small tag for this. And practical efficiency demands that everything around communication complexities of n square kappa, if you want to be precise. And the synchronization mechanism should be efficient, right? What we could do is we could just take a build certificate for every round, saying, collecting signatures saying that, okay, we are all in this round. Let's all enter the new round 100. And if I send this certificate to everybody, the communication complexity becomes n cube. And note that we do not have any threshold setup assumptions, so we can condense this certificate because we want reconfiguration friendliness. So we need a better tag, and the answers to all of these questions turns out to be the PVRS string itself. So the PVRS string, once you open it, it's a constant sized beacon that anybody can use to convince that the PVRS was opened correctly. So that solves our synchronization problem. And basically we needed a new SMR. And we use eraser coding to handle these long inputs that each leader is inputting to the SMR. And we use the PVRS from the leader as input to make sure that to solve the synchronization problem as well. What we also use is a fast path and slow path mechanism. So in the fast path, if in a round, the actual faults are less than 1/4 of the system, the whole round will finish in network speed. So within a few message exchanges. Otherwise, let's say more than 1/4 are misbehaving or not sending messages or doing something else, acting differently, then the actual round may take up to 11 delta. So and both of these paths are mutually they will not result in conflicting values from being committed. I see some questions. I will hold on to it until the end of the talk, so that we can discuss it. Of course, and we our erasure coding and PVRS, all of these are tailored to ensure we tolerate the optimal number of Byzantine failures. With all of these techniques, we get open square communication without actually any threshold setup, which is like the first in our paper, and we get reconfiguration friendliness. So we reach the end of the talk. So at the time of writing, this is the performance. So I'm sure HashRand and others are doing much better now. But at the time of writing, this was our performance. We found that TRAND and BRAND paper, which were the state of the art at that point, we could generate a lot of beacons per second. Key part here is the optimistic responsiveness, right? You could just actually receive messages quickly and under good conditions when the actual faults were less than 1/4, we could actually do very fast beacons because you're not waiting on timeout. It is almost the nice property you get from asynchronous or like non-synchronous protocols, I would say. So yeah, in summary, OptRand has unpredictability of up to only one round. So if anybody is in round 100, nobody knows what the 101st beacon is going to be. Its bias strength has optimal resilience. It has n square communication complex. It is also best latency, right? Network speed, and it's reconfiguration friendly. You can add new nodes in 3+1 rounds. So that's the end of my talk.
Great. It's pretty good on time. So yeah, so there are a couple of questions. I think Aline was pointing to the paper about what I think Shourab talked about it yesterday, that there is a more efficient aggregatable PBSS than script that minimizes number of pairings. It's just a comment. And then there is a question by Amit. Are you using a random oracle in the decomposition proof construction?
Yes. So we use NIZIC to prove that whoever is contributing that PVSS knows the secret that's being shared. So that NIZIC requires the random oracle to be proved correct.
All
for
right,
simulation soundness, yeah.
Fantastic.
For knowledge soundness.
Yeah, I guess I also speculate that. Yeah, anyway, so fantastic. I think we are running slightly late of time, so we can end the session here. Thanks a lot.